we're going to talk about free body diagrams. And free body diagrams are a way that we are going to make a diagram and show all the forces acting on only one object. Now, we can't have a picture of some kind of a scenario and show all forces, because that would be a cascading type thing, because one thing is pushing another thing is pushing another, and with Newton's third law, action reaction, we have all kinds of things, and things would get overly complicated and it won't help us answer any questions. So we always have one question about one particular object and we focus on that object. So we need to show all forces on that one object, and then we're going to use Newton's second law to determine if it's accelerating and if it is accelerating, what's that rate and all that kind of things. Or if we know something about acceleration, we can solve for an unknown force that we have labeled but don't have a quantity for. All right, so let's take a look. So again, all forces act on one object, and we're going to use this to analyze problems. And students really have a hard time with this because every picture is different. The amount of forces that are in a picture are different, and we have to figure out what we know and what we don't know every time with a Newton's second law story problem. But the picture and this free body diagram is really, really the most important thing to know or to do to be able to solve problems. All right, we have two main scenarios we're going to do. One is so the two scenarios, our first scenario is when we have an object that we know is at rest or we know it's in constant motion. Now, how do we know that? It would say a block of wood is sitting on a table, or an object is at rest, or if it's in constant motion, it'll say, object is being pulled at 5 meters per second. All right, something like that, some way that we know it's in constant motion. All right, now if it is in constant motion or not moving at all, guess what we know? We already know some information, and that is that A is 0, all right? And if A is 0, then since F net equals MA, and A is 0, we know that the F net is also 0. So this is gonna allow us to solve problems, all right? So in this case, we will set up our formula so all forces will add to 0, okay? Here is a sample problem. All right, very classic. We always seem to draw lots of boxes with physics. Okay, so here we go. Got a box sitting on a table. If a box is sitting on a table and this box is not falling downward, accelerating downward, then again, we know all the forces must be canceling. And now what forces are there? Well, hopefully we realize the first force is on this box. If this box has mass, then we know it has weight, and if it has weight, then the Earth's gravity is pulling down on the box. Okay, and how do we draw that? When we draw free body diagrams, we normally start the tail of the arrow where the force originates, okay? Not the tip of the arrow on the object, but the tail of the arrow where the force originates. Now, weight or force of gravity is an odd thing. It pulls from the center of a mass. All right, now that's very different. Most of the other forces we do are touchy forces. If you push on a box, then it's on the edge or surface of the box. But weight or gravity pulls on the center. So we're gonna find the center of the box, and that's where I'm gonna choose to draw my arrow. Now, we also know the direction of the arrow, because weight or gravity pulls towards the center of the Earth. And so we're gonna just make that down. Now, how long do I draw this arrow? It's all relative. So however you start one arrow will kind of determine the rest. You could have a whole scale or whatever, but normally we want them just kind of relative. We're doing a sketch. But we do have to be careful just to make the ones that are equal look like they're equal, or if one, and one is greater, we'll see. So how long did I do my picture? Okay, I just did it down to here. So here we go. Now, when I label that I need to label that force so everyone knows what it is, and I'm going to do F sub G, force of gravity. Okay. Now, what other forces are there? Well, so that's one. Then I also, in this problem, have pushed down on the box with 10 newtons. Now, first of all, do you want to do a math already a little bit? Do you understand that if gravity was 10, this is around 40 newtons of force? All right, and we pushed down on the box with 10 newtons. So if we're gonna draw this, so what do we do? You could draw in a picture of a hand if you want. Here's someone's little hand. Okay, it's really bad, but it's okay. All right, so there's some crazy hand down on the box. All right, and so what? So we're gonna draw an arrow. And again, the tail of the arrow is where the force originates, and originates between the hand and the box. So I'm gonna start my arrow, let's say here, and we're gonna push down. And how long do I make this arrow? About 1/4 of this. So whatever, I'm gonna make it like that. Okay, and I'm gonna label it, if you want, force of hand. And if you want, you could say how much that quantity is, 10 newtons. Okay, cool. Now, if this is at rest, that can't be the only forces because they're not canceling, right? So we need a canceling force. And so, and that is going to be our normal force. Remember, our normal force is going to be a force that's perpendicular between surfaces, all right? Between, and in this case, these two materials, all right? So the normal force is going to be upward, and it's going to be, because we can say another word for normal force. In regular physics, I don't use that word normal, I use support. So I'm gonna call it our support force. So we know the table has to provide a support force on the box, otherwise the box would fall. Okay, now how much does it have to? Well, hopefully we can understand and logically understand this problem that it must be supporting with equal the amount of forces down. All right, so I'm gonna take this and this, and I'm gonna draw an arrow equal plus this. All right, so this is Fn. Now that big N is normal, not net. That's not F net. Okay, F net will really truly write F. You can write F net. That's the same as sigma F. You could do that. All right, that's not the same as Fn. Fn is the normal or support force being provided by the table. Okay, so how do we write this into a statement now? What are we gonna do? Well, we've determined already, since the box is at rest, F net is 0 equals MA, if you want, or the other way. Let's do it this way. F net equals MA, and therefore it's M times 0, so 0 equals a sum of all the forces. Look at your picture. We have Fn, Fh, and Fg. And does the order matter? Absolutely not. Okay, so I want to solve for what the normal force is. So I'm going to do Fn. I know the F of hand is 10. Now we have to watch with sign at this point, definitely. And so that's down, so I'm going to put negative 10 newtons. And then my force of gravity, isn't that mg, right? And what is mg? So our m, right, is 4 kilograms times negative 9.8, all right? And so we have, if you want, 39.2 newtons negative, and we have this right here. So if we want to solve for Fn, we just bring that stuff over to the other side, right? A negative 10, so positive 39.2, and so we bring those both over to that side, and we have only 2 significant digits, so we have 39 and 49, so we have 49 newtons, okay? And that's positive, so this is up just like we have drawn there. All right, so this is an example using a free body diagram to help guide you in solving Newton's second law, which is just plain old F net equals MA, to find an unknown that we have there. All right, okay, now our second scenario is if you have an object that is accelerating. All right, so if an object is accelerating, what do we have going on here? Okay, if an object is accelerating, then we don't know A. Okay, so it's a different kind of problem. So we have to have other information. Okay, so we sometimes are given the acceleration. We could solve for missing forces, or if we know all the forces, then we can solve for an acceleration. Either way. So let's look at this example here. We have an elevator, and this case, I give you the acceleration. All right. And I give you the mass of the elevator's contents. That means we know another force. And I want to know what is the tension in the elevator cable. Tension, all right, remember, is force in a rope. Okay. All right. So how about we label some things in this diagram? Let's do our free body diagram. Well, we know, once again, from the center, I'm going to draw in my force of gravity coming from the center, and right, that equals mg, so it would be the mass times negative 9.8. All right, so we have that. Well, tell me this, if the elevator is not accelerating, so if it was at rest, what would the tension in that rope be? Well, if it's not accelerating, F net equals, MA equals 0, and that means whatever the tension, the pull in this rope, okay, FT of this rope would have to be equal and opposite this so that it all adds to 0, okay? But that's not the case here. So tell me about the tension in that rope. What do you know? Well, we know it better be more if this thing is gonna go up. If it's gonna accelerate upward, we have to have a leftover force that can be our spending force to create an acceleration, right? F net equals ma. Whatever force you have left over, you can spend on accelerating. All right, so I know this thing has to be longer than this thing. That I know when I draw my diagram. Okay, so let's do some math. All right, so Newton said F net equals ma, and now we have those things. So I'm gonna write M, what's my M? 920, and my A is 4.5. So I know how many newtons I have to spend on accelerating. What do I know? I know this, I have Fg plus Ft. All right, well, let's do the numbers already. So I have this is 4120 newtons. This is going to be, what do I have? Oh yeah, sorry, 920 times negative 9.8, all right, plus Ft. So 4120 newtons equals, have to look, negative 9016 newtons plus Ft. So when I solve this, I bring this over to the side and it becomes positive, and we're gonna add to that, right? And so I get 13,156 newtons. All right, too many sig figs, and we end up with 13,200 newtons is my force of tension. So again, this has to be bigger than this. Some people will screw up signs, but in the end, if you're gonna lift something upward and make it accelerate upward, you know you have to pull more than its weight. So if your number is less than the weight, you know that's gonna fall. That's gonna accelerate downward, all right? So we can always keep that straight. Okay, so this is the math. I know at this point some people wanna do stuff in their head. I'm telling you, if you don't do things all pretty, it will tend to be a case where, again, you're gonna make mistakes, and you're gonna cause a loss in points, okay? All right, so now we have another example, and of course, we make things a little more complicated, because as we see in this example, we have a pull at not just an X or a Y, but at an angle. So right away, I mean, we can look at this question, but basically we see a few things here. First of all, constant velocity. So constant velocity means this is Yay, one of those problems where just like it being at rest, F net equals 0. So we know all our x's and y's should cancel out. And we have to think about things in x's and y's, definitely in this case, because again, we have a pull at an angle. That ain't gonna work out. We need to change that, right? We can't leave that at some angle. So we know we can fix that. So I'm gonna do my free body diagram. I'm gonna label all the forces and then actually read my questions, because I always wanna know everything there is. And so just label it really nice. First of all, this is all about this wagon or cart. So we're gonna label all the forces on the cart. We don't care about this guy and this guy's feet against the ground and the ground against him and whatever. You could keep going forever, but we're just gonna focus on this cart with this creepy girl that looks like she has black eyes and this guy. Okay, so what do we have going here? Okay, so we have 50 newtons right here, all right? Now, how much of that, right? Let's do something. We need this force of pull in the x direction, and then we definitely want then to label another, right? That we know there is a force of pull in the y direction, although it looks like pulley now, right? Okay, so that's one. Then what other forces are on here? Well, we know the force of gravity exists, so we have another y force, and I'm just gonna leave it from the middle of here, center of mass of the whole structure, we don't really care. So I'm gonna label this, and in fact, I already know, I'm gonna predict this is a bit longer. So why do I think this one is longer than this one? Why wouldn't this be longer than this one? Well, that would mean this very nice, not nice father was lifting this. If this is greater than this, wouldn't she flip? All right, that would be another kind of problem, but that wouldn't be a book style question for sure. All right, so this is force of gravity, all right? That is of this mass, and we already know in the problem it does list the mass there. Okay, so that, we have that. What else do we have going on? Well, we know this guy is not the only thing keeping this from sinking into the ground. The ground has a support force. That support force is also called the normal force, and so that's Fn labeled there. And so we know that's another force we're gonna have. And I'm gonna keep all, I guess, my vertical ones in black, although my black is giving up the ghost here. All right, so I'm gonna, in fact, that's gonna be less. All right, so we know that there is some kind of a normal force or support force from the ground, okay? What else do we have? Well, I know there's friction. Now, why must there be friction? Because without friction, there is only this pull in the x direction. And what did Newton say? Said that if there is just one force, then that means there's an F net, and there's an F net in the x direction, means this thing's gonna accelerate. It's gonna go faster and faster this way. But the problem says you're going at constant velocity. That means this pull in the x direction must be combated by an opposite pull of the same magnitude in the x direction. And that's our friend friction, all right? Friction always opposes. We're gonna have a separate lecture on friction, but we should realize that friction is going to impede motion. So if you pull something this way, friction is back in the opposite direction. And so I'm gonna label that. Now, where should all our arrows, tails, start where the force originates. So you notice I started it there. This is special because it's gravity pulls on the center of an object. All right, this was the contact surface, so we leave there. And then same thing with friction, where I'm gonna pretend like it's acting on this back wheel. And so I'm gonna start my arrowhead there, and I'm gonna go like this, and then I'm gonna label this force of friction, FFR. Okay, so let's do some math now. So for the first question, what must be the force of friction? Ooh, this is a nice one. There's only 2 green arrows here, and I'm gonna make my statement. I'm gonna say F net in the x direction equals ma in the x direction, which happens to be 0. There is no acceleration in the x direction. and it's a sum of my pull in the x direction and my force of friction. I know, or I can calculate my pull in the x direction because this was 50, and I'm going to do cosine of 30. And then I can solve that mathematically, and I have negative 43.3. Oh, why is it negative? Why is it negative? Oh, wait. That one isn't negative. Excuse me, because I'm not done yet. So this is 43.3. I was stepping it up. I was already thinking about this one. So we have 43.3. We have force of friction equals 0. So if I'm going to solve for my force of friction, it would be negative. And I think we only have 2 sig figs. All right. So this is because it's to the left, right? And it's opposing this force that's going to the right. All right. Easy peasy, right? 2 forces. We know they have to add to 0 because it's at constant velocity. All right. So what about the next part? What about the normal force? Oopsie. Uh-oh. Uh-oh. Accidentally got rid of my gravity. Okay. And my F. All right. So what do we know in this case? I'm going to have to do this in a different color because it's just not. Oh, that one's not working either. We'll do it in brown. Okay. So what do we know? In the y direction, F net in the y direction. All right. This is an assumption, but it's a pretty good one. Since the problem doesn't say she's, again, being flipped into the air or falling through the ground into a hole, then we're going to assume that mass times the acceleration in the y is 0. The sum of all the forces is 0. And what do we have? All 3 of these. We have Fn, Fg, and F pull in the y. Doesn't matter what order you write these. I wrote them in the order that I had them written here. So 0 equals we don't know. This one we can find out because the mass is 15, right, times a negative 9.8. Then we have to find out the y. So we know that's 50 sine of 30. All right. This is negative 147. And then this part is 25. Okay? And so we're going to move this over. This becomes positive. When this moves over, it becomes negative. So these are subtracting and change sign. And when you do that, Fn equals 122 newtons. Okay? Oh, and I guess if we only have 2 sig, we got 120 newtons. All right. So this ground has to support with 120. All right? Because this is lifting somewhat up, but not enough. There's not enough to support all the weight. So this is the support left over. In other words, the ground thinks there's only a weight of 120 that it needs to support because it didn't know that something. This is kind of like if you weigh something on a scale and you lift a little bit up on it, it doesn't the scale does not feel the full weight of what's on there. Okay? All right. So always think about first of all, draw all the forces. Think about the lengths. Do make it kind of relative. I guess I made this was pretty big compared to this. This should have been drawn a little bit longer than that. And then look to evaluate. You have to decide, does F net equal MA and A is a known number, or is it F net equals 0 and all the forces should cancel? All right? Okay. Good luck.